In this video, we're going to motivate something called the expected value. And the expected value is a more general term for what we've called the average or the mean of a data set. Now remember that when we have a large set of data, it's very difficult just to look at the data and see what's going on, especially if there are thousands of values, or even tens of values for that matter. An average is a way to take that data set and reduce it. It's called a data reduction method. And we get a single value that sort of tells us how, on average, those values appear. We're going to give that a little bit more meaning in this video. So an expected value is a more general way of computing a mean when the weights on the values are potentially different. Let me give you an example. Let's say that you and I play a game where you're either going to give me $2 or I am going to give you $4. Okay, what's the trick here? Well, let's add some more detail here. First of all, you giving me $2 from your perspective is a loss. And so I'm going to put a minus sign in front of that $2. And you receiving $4 from me is a gain to you, so I'll denote that as a positive $4. And let's say that what we're going to do is we're going to toss a coin. And we decide that if that coin comes up heads, you're going to give me $2. However, if that coin comes up tails, I'm going to give you $4. Well, this seems like a pretty good game because if we play 10 times, then we would expect the following outcome, roughly. Roughly speaking, we would expect that there would be 5 heads and 5 tails, although we know that that could be 4 and 6 or 6 and 4, maybe even 3 and 7, 7 and 3, well, potentially even 10 and 0. But oftentimes, if we toss a coin 10 times, we're going to get roughly 5 heads and 5 tails. So if 5 times heads comes up and 5 times tails comes up, then those 5 times that we got heads, you're going to pay out $2. Well, that means in total, you're going to lose $10. That's the bad news. But the good news is that 5 times tails came up, and 5 times 4 means you're going to get $20. Okay, so in net, you came up with a gain of $10. $10 net gain. And if we average that out across the 10 times we played, per 10 tosses, then you actually gained $1 per toss. And that's not bad, right? So every time you play, on average, not every time, sometimes you're going to lose $2 or you're going to gain $4, but if you took out your winnings and you spread them across all of those 10 tosses, you really gained, on average, $1 per toss. So the average of these two values is really just negative 10 plus 20 divided by 10. But let's say that I threw a little wrench in this game and you thought I was playing fair, but in fact, I had a coin that actually came up with tails only 1/4 of the time and came up heads 3/4 of the time, or 75% of the time. Well, that changes the dynamics of the game a little bit because you're going to be losing $2 more often than you're going to be gaining $4. And as we begin motivating this concept, that is the purpose of the expected value, to help us figure out how do we take into account the 3/4 and the 1/4. An average up until this point has assumed that each value has an equal weight in the average process. An expected value allows for those values to carry different weights. So in our original example here, each outcome carried 1/2 of the weight. But in our updated, revised game, heads carries a higher weight than tails. So losing $2 is going to occur more often than gaining $4. Let's come back to this example and go back for a moment to the idea of just an average. And really interpreting what this average actually means, other than to say it's the middle value or it's the sum of the values divided by the number of values. Suppose you and two friends pool your money together. You and your friends reach into your pockets and produce the following: $10, $20, and $30. What is the expected value and how can we interpret this? Well, there's one instance of $10, there's one instance of $20, and there's one instance of $30. Right, so when we compute an average, we add those values up and we divide by the number of values there are. Okay, so I'll say that this is 3 people is our unit for the 3. And the numerator we can think about as, hey, this is us putting all of our money into a pile. So what we're doing is we're pooling our money. And what that means then is that if we pool our money together, we have a pool of $60. And now we have this division by 3. Now it's 3 people. And when we divide, we're breaking it up into 3 even groups. So split into 3 even piles. And this means that each pile would constitute each person receiving $20. So yeah, we could say on average we have $20 per person, but another way of thinking about this is as follows. If we pooled our money and divided it equally, among us, each person would get $20. Now, whether we're dealing with money or we're dealing with test scores, if these were test scores out of maybe 30 points and a person scored a 10 out of 30, a 20 out of 30, and a 30 out of 30, and we said on average that person scored 20 out of 30, well, what we're really meaning is that if we were to redistribute the points so that each score was the same, then each score would be 20 points out of 30. So I like to picture it this way. One person has $10, another person has $20, and another person has $30. And that's what these bars represent, the height representing how much they have. And if we were to redistribute all of the money, then one way we could think about this is, well, we're gonna sort of take off the top portion of what this person has here that has the $30, and we're going to stack it so that we even out the distribution of money. Okay. Doesn't matter whether it's test scores or it's money. The idea is that we're pooling and redistributing. Test scores, we pool them all together, we redistribute them so that we can come up with, if all the test scores were the same, here's what they would be. Now I want you to think about this as in one more way. When first of all we write notation for the expected value, these are what we would refer to as our x values. And we can say this in one of really a couple of different ways. We could say the expected value of x, of the x's. Okay, well, often we write it like that. Sometimes you can use parentheses around the x. And what this is sometimes called x with a bar over it, although we're going to stick with something a little bit more, or a little bit less conventional, which is to use the Greek symbol mu. This is the Greek symbol mu to denote average. And to calculate this, we're going to add up, okay, that means add up, sum up all of the x values and divide by the number of values. And we'll say that there are n values. This is the number of values. Okay, well, another way I could actually conduct this computation right here is instead of adding them up and dividing by 3, remember when we have a fraction, we can think about splitting this fraction up into 3 separate terms, namely 10 over 3 plus 20 over 3 plus 30 over 3. Okay, now why would I write it that way? Well, I am actually going to convince you that these 3 values have equal weights. In fact, taking 10 divided by 3, and then you can think common denominators here. Normally we would take these 3 fractions and combine them into 1 by adding the numerator since they have common denominators. But I'm going to write it as 1/3 times 10. 10 divided by 3 is the same thing as saying what's 1/3 of 10? Plus 1/3 of 20 plus 1/3 of 30. Now these values that we have here, these 1/3, these are considered to be what we call the weights. And the key here is that they are the same. Right? These are the same weights in this instance because there are 3 people. Each person's input carries the same amount of weight is one way to think about that. Let's change up this problem just a little bit. Suppose there are 10 friends. 5 of them have $20, 3 of them have $10, and 2 of them have $30. Now we can find the expected value in one of 2 ways, right? One way would be to say, well, what I'm going to do is I'm going to take 20 plus 20 plus 20 plus 20 plus 20. So that's the 5 people who have $20. 3 of them have 10, so we're going to add their 3 10s into the pile as well. And 2 of them have 30, so we're going to add those 2 30s. Now we're going to divide that whole pool among 10 people. So we have dollars up here, and then we have among 10 people down here. Well, that's a very tedious way to do it. In fact, a better way might be to say, well, I have 5 20s. I have 5 instances of 20, 5 times 20, plus I have 3 instances of 10, plus I have 2 instances of 30, all divided by 10. Now, if I implement this other way here, then I can actually split this up into 3 separate fractions, 5 times 20 over 10, or 5/10 of 20, plus 3/10 of 10, plus 2/10 of 30. All right, so I'm kind of going straight to this step right here and saying that really now I actually only have 3 values. I have this, I can consider this my x1, my first x value, my second x value, and my third x value. And notice that each value has a different weight. Different weight. Okay, why do they have different weight? Well, first of all, the 20 has a higher weight because half of the people are contributing that amount. The 10 has a lower weight because 3 out of the 10 people are contributing that amount. And $30 has the lowest weight because only 2/10 of the people are contributing that amount. And notice that we can use the traditional average, adding up all 10 values and then dividing by the 10 values. Or I can just say there are really only 3 distinct values and I multiply them by their corresponding weights. Now, I'm not actually going to produce the result here because the point is that if I know that there are 3 amounts, I can just multiply each value by its corresponding weight to come up with the mean. So where do we actually see this kind of thing? Well, let's look at one instance, and one really important instance in what we call actuarial mathematics is determining what the expected value is on a warranty contract. So a warranty contract is just an agreement between a company and a purchaser that says, hey, if you pay us this amount, then we'll insure your product for you. And there's a risk, right? There's an uncertainty, whereas up here in our averages, there was no uncertainty. Here there was no uncertainty because we knew exactly what each person was contributing, and we knew what each person would get exactly, and same in example 1, assuming that money would be redistributed. The company sells a warranty on a digital tablet. The warranty is for 1 year. The cost of the warranty is $50. A purchaser of the warranty can file up to 1 claim for any problems experienced. In the event of a claim, the company will pay the filer $300, the full replacement cost of the tablet. All right, so I can pay the company $50, and if something happens in my tablet, I file a claim, the company pays me $300. The company has found through data collection that 5% of people file a claim during their warranty period. All right, so notice that paying out $300 is not as likely as collecting the $50. They're going to collect $50 from everyone, and only 5% of people are expected to be paid $300 by the company. So already we can see that these two different outcomes are not going to carry the same weight. What is the expected value in dollars gained or lost per warranty contract? Well, let's set this up again 2 ways. One way is to think about the fact that if we had 100 people, I pick 100 people because we're talking about percentages here, then what I would expect is that 5 people would file a claim and 95 people would file no claim. Well, for the 5 people that file a claim, let's see what they pay versus what they receive. Okay, so for the 5 claims, we're still going to collect $50. The company still collected $50 from them, so they gained 5. I'm going to put a plus here because this is a gain of $50 5 times. So they collected $250 from the filer, from the person buying the contract. Versus over here, the 95 people who don't file a claim, they still pay the $50, but there are 95 of them that pay. So far everything seems to be good for the company. However, the people that did file the 5 claims, the company had to pay out, they lost $300 on those 5 contracts. So they gained $250 from them, but they lost $300 from the fact that those claims were filed. So $300 times 5 people is $1,500. So they lost, let's still have that negative sign there, they lost $1,500, they only gained $250 from them. So that means that in net, they came ahead they lost $1,250. Now on these 95 claims, we just need to compute what is 50 times 95, which is $4,750. Okay, that's the bottom line for those 95 people who didn't file a claim. We lost $1,250 on those that did file a claim. So in net, we came up with a loss of $1,250, a gain of $4,750. Now that's a total, that's the total gain. We can see this can be a positive number, but we want to know the expected value per warranty. So what's the average that they lost or gained on each contract? Okay, well we use the 100 here to indicate, let's look at this for 100 people or 100 contracts. 4,750 minus 1,250 is $3,500 gained in net. Divided among 100 contracts, on average, that comes out to $35 per one contract. That answers our question right there. We came up with $35 per contract. Now, to think about this in a more mathematical way, another way we could have thought about this is we have outcomes, and then we have the likelihood or the probability of that outcome. Now, again, not exactly 5% of people are going to file a claim, but that's the only data that we have to go off of. So we're going to make the assumption that approximately 5% of people are going to file a claim. Now, you might think that this 100 was very particular and that this $35 per contract was particular to 100 people, but notice that 5 divided by 100 is still 5%, and 95 divided by 100 is 95%. So the outcomes are that we either have no claim or we have a claim. Now everybody, let's think about this at the individual level. A person that files no claim is going to pay the company $50. So the company is going to gain $50. If there is a claim, well, they're still going to collect $50 from the participant of the plan, but they're going to lose $300 on that participant because of the claim being filed. So if there is a claim, the company loses $250. Now, as far as the probability goes, we know that the likelihood of filing a claim is 5%. So I'm going to write that as 0.05. You could also write it as 5 over 100. So that value that negative 250 only gets a weight of 5 100ths, whereas filing no claim gets a weight of 95 100ths. So we can come back over here and notice that our coin toss example, we just had, instead of having weights of 1/2 and 1/2, we had 3/4 and 1/4. So we'll come back to this to see whether that is a fair game for you as the player versus for me as the player. Okay, so my outcome of 50 occurs 95% of the time. So 0.95 or 95 100ths times 50 plus 0.05 times negative 250. And lo and behold, this comes out to 35. Okay, this comes out to 35, which is exactly the same value we came up with over here. Now, because this isn't, the 35 represents dollars, and we're dividing this across contracts, this is still $35 per one contract. And it's a positive number, and so that means that we're still gaining $35 per contract. So we now have an intuitive and more mathematical way to compute the average when our outcomes do not carry equal weights. So think about this as a game where the company is going to receive $50 95% of the time, but they're going to give away $250, but only 5% of the time. So there's a higher severity on the loss, but there's a much higher frequency on the gain, right? High frequency on the small gain, high severity with a low frequency. So coming back to our coin toss example, we could think about this in one of two ways again. We said that 3/4 of the time, 75% of the time, you are going to lose $2 versus 1/4 of the time you're going to gain $4. So 75% of -2, this comes out to -1.5 plus 1. So actually now, on average, you are going to lose 50% per one toss on average. Interesting, huh? Here's another way of thinking about it. If we did 4 tosses, then we would expect to get 3 heads and 1 tail. Every time there's a head, you're going to lose $2, so 3 times you're going to give away $2. And then every time there's a tail, you're going to receive $4. So that's going to be a loss of $6 across those 4 tosses, a gain of $4 across those 4 tosses. In net, that's a loss of $2 across 4 tosses. Well, check this out. $2 divided into 4 pieces is exactly 50 cents. A loss of 50 cents per one toss on average. So if you were to take all of your losings and average them out, equal them out across the 4 tosses, you would have lost 50 cents on each toss. So the difference between an expected value and a regular mean is that now we have a way of incorporating the fact that there are these varying weights.